Hello, I want to show you this graph of pH against volume for the titration of a weak acid, acetic acid, with a strong base, sodium hydroxide. Let's see what happened during this process. And you can compare the shape of this graph, which is called the titration curve, with the previous one, which was the titration of a strong acid and a strong base. This is the titration curve for the titration of a strong acid and a strong base. So let's work with this titration. Again, this is a titration of a weak acid, acetic acid, with a strong base, sodium hydroxide. So we have initial concentration of acetic acid is 0.200 molar. Look at the pH. Let's see if that makes sense with the initial concentration. We have initially just acetic acid in the flask. I'm going to use the simplified form of the acetic acid plus H2O. To form the hydrogen ion plus the conjugate base. We said the initial concentration is 0.200 molar. And we know the Ka for this weak acid, you can remember, is 1.8 times 10 to the negative 5. So you have that on the flask initially. It's going to be on your measure flask. You add, it says here, 25 mLs of the acetic acid solution with that concentration, 0.200 molar. The question is, what is the initial pH of the solution? If we place a pH meter here, it should give us this value. So let's calculate that. And this is also a good exercise to show how to calculate the pH of a weak acid. So we draw, in order to do that, we draw the ice table. This is the initial, so initial is 0. The change is minus x, plus x, plus x, and the equilibrium will be 0.200 minus x, x, and x. The equilibrium expression for this Ka is Ka equals x squared over 0.200 minus x. And that is equals to 1.8 times 10 to the negative 5. Again, we're expecting x to be a very small number compared to the initial concentration of acetic acid, and taking into account that the Ka is very small. So we are going to do the approximation and say that 0.200 minus x is about the same as 0.200. And that will simplify our process. And that is going to be less than 5%. So we're using the 5% rule. So we can solve the equation, and we'll have x squared over 0.200 equals 1.8 times 10 to the negative 5. And as you can remember, I gave you another trick that will simplify your work. So concentration of H plus for the weak acid, which is your X, because that's what you're finding here. X is your concentration of H plus, equals square root of Ka times initial concentration of the acid. That means we have a square root. We take the square root of 1.8 times 10 to the negative 5 times the initial concentration, which is 0.200. We do the operation, and we find that concentration of H plus equals, let's see, we have 1.8 times 10 to the negative 5 times 0.200. And that is equals to 3.6 times 10 to the negative, let's see here, 1, 2, 3, 4, 5, 6. 3.6 times 10 to the negative 6. So we have 3.6 times 10 to the negative 6, and we take a square root of that. We take the square root of that number, and that will be 1.89 times 10 to the negative 3. 1.89 times 10 to the negative 3. That is the concentration of H plus of that initial concentration. So the pH will be the negative log of 1.89 times 10 to the negative 3, which is, we go back to the calculator, we just take the log of that, and that will be, since we have negative log, therefore the pH will be 2.72. And that's exactly what we have here. 2.72. That's the initial pH of the solution. and you start titrating using the strong base sodium hydroxide. And look at the slope of this curve. And we are going to realize that when we titrate the acid, something else is going to happen there. And that's the analysis we need to make every time we do a titration, especially when you have titration of weak acid against a strong base or a weak base against a strong acid. So we have the weak acid HAC plus sodium hydroxide, aqueous, to form the salt, sodium acetate in this case, plus water. Right away, I know you realize something. So every time, once we start the titration, you add the sodium hydroxide and you get this. Do you realize that at that moment, or any moment when we add sodium hydroxide, we are going to have portions of a salt containing the conjugate base of the weak acid, and also we have weak acid. So we have the two elements that are very important to make a buffer. So during the titration of weak acid with a strong base, during the first process of titration, before the equivalent point, you are actually making buffer solutions. Because every time you add the base, you have the acid that has not been neutralized, and also you have the salt or the weak acid after neutralization. So the two basic elements of a buffer, so it's going to behave like a buffer. And we can find the pH manually at any point just using Henderson-Hasselbalch equation. So you can find the pH at any time using the equation, as you can remember, equals Ka plus log of concentration of the salt over concentration of the acid. So this is how you find the pH at any moment for the solution during that titration until it is fully titrated. So here shows the flat line. On the middle of the flat line, we get the equivalent point, and happens to be not 7. Like on the previous one. On the previous one, we have the equivalence point pH 7. Why? Because this titration between the strong acid and the strong base forms a salt that is neutral. It's neutral because it's made of two ions that are too weak to react with water. However, in this new titration, the reaction is actually producing acetate ion. And the acetate ion is strong enough to react with water. So every time that the ion is being produced during the titration, the ion will react, will hydrolyze with water. To form plus OH minus. So the hydroxide ion, which is the most basic species you have in the world, causing that solution to be basic. So at the equivalent point, look at the pH, it's basic. Because the reaction is making a basic salt. So this is the most important part of the titration. And this is to remind you that when we're doing titration, we have to be careful with what kind of titration we have. Different possibilities. You can have a titration of strong acid, like for example, HCl, and strong base. You can have a titration of strong acid against a weak base, like ammonia. You can have a titration of a weak acid, like acetic acid, against a strong base. Or you can have a titration of weak acid against a weak base. This titration will produce a neutral salt. So at the titration, at the equivalent point, the pH is going to be 7. On this one, also will form a buffer during this transition of neutralization. And at the equivalent point, the pH will be acidic. So the pH will be less than 7. Because remember, this forms an ion. The conjugate acid of the weak base, which is NH4, reacts with water to form NH3 plus H3O plus, and this hydrogen ion will lower the pH of the solution, so that at the equivalent point is going to be less than 7. This reaction here, as we just did, at the equivalent point, the pH is bigger than 7. In our case, is 8.88. And this reaction also will produce a buffer. And the pH will depend on the relative concentration of those two and the relative strength. Both have about the same strength. This is 1.8 times 10 to the negative 5. And this, the Kb for this Ammonium is 1.5 times 10 to the negative 8. Happens to have exactly the same, about the same. We rounded off to the number. Values for Ka and Kb. So this ended up being practically neutralized because both have same strength. All right, so this is how you do analysis of a titration curve. This is another situation and very helpful to understand the process to reach the equivalent point of titration. And I'll show you here on this one. This is actually a technique used to find the Ka of a weak acid. And that is done by finding half of the equivalence point. So you do the titration, you draw the graph, and during the next lab, you will see how it's done. Using the potentiometric titration, you put the probe, pH probe, connected to the computer generates the graph. Once you have the graph, you find the equivalent point, which is half of this flat line here. That will be your equivalent point. And we want to know what is the Ka for the acid. So you find half of the equivalent point. So in the equivalent point, for the equivalent point you use here 15 mLs of the base, half, we'll use half of the volume. So you find the half equivalent point, reach your curve, and extrapolate, find the y-intercept, and that will be the pH at half equivalent point. What do you do with that pH at half equivalent point? You do the same thing here. For this one, well, it's not exactly straight line, but let's assume, don't be too hard on me for this straight line. That will be the pH at equivalence point, the one we were just talking about. So you find half of that and find what is the pH at half of the equivalence point. And that is important because when we plug that into the equilibrium expression at one half of the equivalence point, the concentration of the weak acid equals exactly the concentration of the salt. That makes sense, right? So you have the weak acid, you be titrating that weak acid with the base, and will form the salt containing the conjugate base of the acid plus water. So once you have titrated half of that, you will have generated also half of the conjugate base. So the two at half equivalence point, you have equal amounts of the weak acid and the conjugate base. Knowing that, we can plug that over here on the equilibrium expression, and these two values cancel out because this is the same. Let's say 1 and 1 or 5 and 5. Whatever the concentration, they are the same, so you can cancel out. So the tricky part is once you do that, once you find the concentration at 1/2 of the equivalence point, and you know the pH of that, that is exactly equals to Ka. So Ka will be concentration of H+. Therefore, pKa equals pH. If we go back, using this trick, simple technique, which is called titration to find half of the equivalence point. You find the pH of the weak acid, and the pH of the weak acid is exactly the pKa. Here we have it, pH, there. So the pH, the pKa, and once you know the pKa of the acid, you can find the Ka, because Ka then for the acid will be equals to 10 to the minus pKa. Very important technique, very simple. Just do the titration, do the graph, find half of the equivalence point, find the pH at that point, and that will be your pKa. Your pH equals pKa, and find Ka. You see, very simple. This is a titration of the weak base ammonia against strong acid. Same thing, during this process, what you have is a buffer solution, so you can find the pH at any point using Henderson-Hasselbalch equation. The equivalence point, as we predicted, should be acidic, because during this process, you are making, the reaction is producing the conjugate acid of the weak base, which is a acidic salt. And this is a typical graph for a polyprotic acids. When one acid has more than one proton, and you do a complete titration of the acid, you get a graph of this with 2 inflection points and 2 equivalent points. And this is called the first equivalent point for the titration of the first hydrogen of the polyprotic acid, and this is going to be the second equivalent point for the titration of the second hydrogen. So you will have, for example, H2CO3. Remember, it goes to titration of the first hydrogen will produce your first salt, which is HCO3 minus plus water. I'm including the sodium because sodium, again, is just a spectator ion, so that you can add it there plus sodium. So the titration, once all this first hydrogen is being titrated, you get here the first equivalent point. And then you continue adding the sodium hydroxide and then we'll start titrating the second hydrogen, which is this. So that one goes through a second titration, second step of titration, which is CO3 minus plus more sodium hydroxide to complete neutralize all the hydrogens. So you will get the carbonate salt plus water, and of course more sodium plus. If we don't know what is if we have a known weak acid and we don't know what is the Ka of that weak acid, we can use the same procedure, the technique called half the equivalence point. So you can find the half of here, half of this distance, this volume, so somewhere here, or here, find out the pH. So that will be pKa 1. From here, you can find the Ka of the weak acid. For this first neutralization. And then you find half of the equivalence point for the second titration, which is going to be somewhere here. And the pH, let me try. This is not too bad. Yeah. So there is going to be this pH here is exactly the same pKa for the second neutralization. Therefore, you can find the Ka2 for that second neutralization. This is going to be the 1, and this is the number 2. So very interesting ways to find in the lab those values like this. Indicators, we talked about indicators already, so you can go back to one of the previous videos to check about acid-base indicators. Our next chapter will be, oh sorry, not the next chapter, the second part of this chapter, chapter 17, and we call it chapter 17b. We're going to discuss, we continue doing equilibria of acids and bases, but now we're going to talk about solubility and simultaneous equilibria. So far, we have mentioned that some salts are soluble in water and some salts are not soluble in water. And we label this as non-soluble salts. But that's not totally true. Because even if they don't dissolve in water, apparently, when we go to the microscopic submicroscopic level, we find that they may have some kind of solubility. Very small, very tiny small, but they may be soluble up to some extent. And that's what we are going to talk about here. Let's see this example. Silver chloride is a white solid. It's not soluble. In general, we say it's not soluble. It's a salt that comes from the reaction of any soluble salt containing silver. And we know that soluble salts usually contains nitrate. So one way to have a soluble silver ions is using the nitrates. So I will use silver nitrate, Ag, NO3, aqueous, and that will be soluble. So you can put that on a test tube, and it's going to be clear, colorless. That means it's completely soluble. And another source of chloride, it could be hydrochloric acid, why not? Aqueous. Also, it forms a clear, colorless solution. When we combine these two together, what's going to happen? It's going to form a salt. In this case, Ag, Cl, silver chloride. So you put them together, this one and this one, and you see right away it becomes cloudy, milky. Why is that? Remember when our first experiment, we get something similar, get milky, cloudy. Cloudy solution, or milky. We say it's milky solution. Because this new compound formed during this reaction is actually solid. It's not soluble, it doesn't dissolve in water. That's why it stays suspended, the solid stays suspended in the water, and eventually it will settle down as a solid on the bottom. The next byproduct is HNO3. So this is solid. It's not aqueous because it doesn't dissolve in water. And that's why we say silver chloride is insoluble. In this section, we're going to analyze what happened with those insoluble, so-called insoluble salts. And we are going to measure the solubility. How much are they soluble? And factors that affect the solubility of those insoluble salts. This is important to know because a lot of ions can be dangerous in our body, especially metals. And they can be present in very small amounts in our body, and they can become toxic. For example, lead and mercury, they cause a heavy metal poisoning. But on environments also, there are some substances that can be very toxic for environment at very low concentrations. So let's do that. Silver chloride here, when you take that solid that you made from the first reaction and you dissolve in water, or at least you put in water, some will break down, some ions will break down. Ag plus, aqueous, Cl minus, the minus is here. Aqueous, that means this is already soluble. You see the solid here is not, this side is the solid, it's not soluble, but once we add the water is here, right? We add the water, because we have aqueous, and the water helps to take some ions in solution. If we write the equilibrium expression for this, you remember the first, one of the first things we did? That will be equilibrium expression will be initially concentration of Ag plus times concentration of Cl minus over concentration of AgCl. However, remember we said that solids are not included into the expression because the concentration of solids are constant, so that's part of this constant. So the expression will be better represented as concentration of Ag plus times concentration of Cl minus. And that expression is called Ksp, the solubility product constant, and will help us to understand how these solids dissolves in water. We are using water as a solvent. And that Ksp for this particular reaction has been measured, and we are going to use those numbers. They are constant and they are given on tables again. You can find these tables on the back of your textbook. And that table is called the solubility product constant table. It will list a number of insoluble salts and their Ksps. But before we start solving those problems, let's clarify some concepts. We're talking about solubility. So let's define that. What is solubility of a salt? It's the amount of salt that dissolves in a given amount of solvent to produce a saturated solution. The molar solubility that we represent using letters S and X is the number of moles of salt dissolved in 1 liter of the saturated solution. So the solution must be saturated. How do you achieve that? So we have this. We have water, pure water, then you add the salt. Let's take the same case of silver chloride, AgCl, solid. And we have water here. At a specific temperature, right? Because we are going to see the temperature plays an important factor during the solubility. Let's say at 25 degrees Celsius, room temperature. And we had that experience of the effect of temperature on solubility. Let's say you're trying to make a lemonade. To drink a delicious lemonade in one of these hot days. So you have 2 options. You can take water at room temperature. Probably it's going to be a temperature higher than room temperature. And let's say you take water at room temperature. So you add the sugar and dissolve the sugar. And you stir and stir and stir until all the sugar is dissolved, and then you add the lemon juice. You squeeze your lemons there. You can do it in any order. Or you can take a very cold water and then you add the ice to cool this down. Or you can put it on the fridge and let it cool. So you prepare your lemonade ahead The second way is when you are on a rush and you take a jar and fill it with cold water and you add the ice right away. And then you add the sugar. And you stir and stir and stir, and the sugar seems like it doesn't dissolve. Yeah, that's the point. Temperature affects the solubility of the solids in water. The higher the temperature, the higher the kinetic energy, the higher the collisions. So the higher the solubility. That's why in every problem it tells you the temperature. Because if you change the temperature, then the solubility will change. So you have the water and you add your solid and you add enough and you will see this milky. But after a while, most of the solid will settle down on the bottom and you will see a fine, like dust material on the bottom, which is the undissolved salt. And you stir again, and then you mess that up. All the particles go suspended, it gets milky again, and then you let it rest, and the solids again will settle down to the bottom. And you can say now you have a saturated solution of that. So the solution gets the maximum saturation at that temperature. But it is important for this process to have some extra undissolved solid here, so that can produce, establish an equilibrium between the two phases. So let me make this bigger. Let's suppose you add a lot of that solid, knowing that not everything is going to dissolve. So most of your insoluble salt will be here on the bottom. Your crystals will contain the components of the material, AgCl. So it's solid, it's together, still solid. And on top of that, fine particulate, you have the saturated solution. Very few of those were able to dissolve, forming the ions in the solution, Ag plus, aqueous. And Cl minus, aqueous. Right there. So the system at that temperature will establish the equilibrium between the solid phase and the aqueous phase. And the ions will start to come and go. Some will dissolve, will become aqueous, and some will come back to solid. Remember, how do you call this? A dynamic equilibrium. So this is one of the conditions for a dynamic equilibrium. You need to have some solid on the bottom to let it establish the equilibrium. And you let it settle this for a while. It takes time. 1 hour, 2 hours, 3 hours, depending on the chemical. So you can measure the molar solubility as the number of moles of the salt that dissolve in 1 liter of that saturated solution. And we represent the molar solubility as S or X. I'm going to use X as my molar solubility on my problems. Some textbooks can use lowercase s for solubility. So we can use the constant KSP to predict solubilities, and or if we are able to measure the solubility, we can find the KSP. And you will have one lab next week finding the solubilities and finding the KSP of different insoluble hydroxides. Again, we are going to use the ion product. Remember when we were doing chemical equilibrium chapter, we were able to find the equilibrium constant, but also we were able to find the reaction quotient was similar to this. Now we call ion product, which is the product of molar concentration of the dissolved ions of the solute. Not necessarily at the equilibrium. So here is the first problem, and I'll show you how to solve this type of problems. So it says copper 1 bromide has measured a solubility of 2.0 times 10 to the negative 4 moles per liter at 25 degrees Celsius. Calculate its KSP value. So in this case, solubility is given, and we need to find KSP from that. So those are the steps. So it says, first, write the ionic equation and the expression for the solubility product constant for copper 1 bromide CuBr. So that's the first thing. Take the formula from here, or the name, and you need to remember, probably it's a good idea to review how to name compounds or how to read formulas. So you see copper 1 bromide, the formula is CuBr. Not always the problem will give you formulas, will give you the name. So you should be able at this time, you should be able to draw the formulas from the name. So copper 1 bromide is CuBr solid, and this is the equilibrium with its ions that way, and that's the stoichiometry, 1 to 1. We draw the expression for the solubility, which is KSP equals concentration of Cu plus times concentration of Br minus. And since solubility is given, remember this substance will make some of these ions soluble. I'm going to use the X. We produce X solubility of copper and X solubility of Br minus. And that X is given. That's the solubility, the molar solubility. So that will be the solubility for copper, which is the same as solubility for bromide, because the stoichiometry is 1 to 1, equals 2.0 times 10 to the negative 4. And we just plug that into here. That number times that number, which is that number squared, and you find KSP 4.0 times 10 to the negative 4, and no units are needed. No units. Units are meaningless. This is the expression of equilibrium constant. All right, this was very simple. Let's do one more. KSP value for copper 2 iodate is 1.4 times 10 to the negative 7 at 25 degrees Celsius. Calculate the solubility at 25 degrees Celsius. The temperature is given, but that's extra information. You don't have to do anything with that. So this time, KSP is given, and we need to find the solubility. So we do the following analysis. Again, the first thing you need to do is to write the complete ionic equation for that process. So this is your insoluble salt, which is solid. You put on water, dissolves into some copper plus and some iodate ions. Be careful with the stoichiometry. 1 mole of this makes 1 mole of copper plus and 2 moles of iodate ions. So the solubility will be X moles per liter of copper 2 plus and 2X moles per liter of iodide. We write the expression KSP, so KSP for that, and here is where a lot of people make mistakes. They forgot to use the stoichiometric coefficient as exponents. So it's going to be, remember we are just writing equilibrium expression, mass action expression. Concentration of copper 2 plus times concentration of iodate square, because we have the stoichiometric coefficient to here. And then we plug that over here. Another common mistake on this type of problem is people not using parentheses. So solubility copper plus is X times, and put parentheses here, 2X and that square. The common mistake is writing that as X times 2X squared. And people will end up doing this, 2X squared, or 2X cubed. And then they will say, why I'm not getting the results? Because you are not using parentheses. When you use parentheses, you will realize that this, when you work this step by step, so remember this is wrong. So that will be 2 times 2X, which is the solubility of iodate, but that, according to this expression, is square. When you work this out, that will be 2 times 2 squared is 4. Let's put it there. Parenthesis. 4x squared. Oh, hold on. I missed the x. I put, it's not 2, it's x. I don't know what you told me to write 2. X. X times 2x squared. That's what I'm doing here. So that over there will be x and this operation here will be 4x squared. And now you can solve it. All right, now that would be 4x cubed. Big difference between this one. All right, this is half of what you should get. Anyway, just find x. Yeah. Put it that way, find X, and you find that X equals 3.3 times 10 to the negative 3, which is the solubility, X. These problems are really not complicated because we already know how to do ice tables, how to do mass action expressions, how to handle equilibrium constants. This one. But I can leave this for you to solve it. I don't want to be that selfish, doing everything by myself. Here is the answer. So do it, try it, and then compare the answer with my answer. We have a special case, a special situation here. Look at this problem. It says calculate Did we do this before? No, we didn't use that before. PVF2, lead 2 fluoride. Calculate the molar solubility of lead 2 fluoride in a 0.10 molar PV lead 2 nitrate solution at 25 degrees Celsius. So let's see what happened. What is the first step? I told you, write the ionic equation for the process. So which one is urine soluble salt? This one. Is this urine soluble salt? It's kind of insoluble. It's a nitrate. Nitrates are always soluble. And also it says you dissolve this into that, and this is already a solution. So you have a solution already containing 0.10 molar PVNO3. And you can notice this is soluble, very soluble. So once you put that solution here, all what you have are PV ions, PV2 plus ions, and nitrate ions there, because they are soluble. And on top of that, you are going to add your insoluble salt. This is insoluble, this one. It says calculate the molar solubility. We find molar solubility only for insoluble salts. You don't want to spend time trying to find the molar solubility of sodium chloride. Why not? Sodium chloride is completely soluble. Anyway, so you add this and you write the equation for this. So let's write the equation for that salt, PV F2 solid in equilibrium with its ions, which is PV 2 plus aqueous plus 2F minus aqueous. And the solubility there is going to be X and 2X. But we have a situation here. What situation you see? That you are adding this insoluble salt into a solution that already contains soluble ions that are common to your insoluble salt. So this insoluble salt, once this dissolves a little bit, is going to form some PV2 plus ions, you see? So at the end, in your solution, you will have two sources of lead 2 plus. One that comes completely from the soluble salt, and one that comes from the solubility of your insoluble salt. And let's see what happens with the solubility. So we need to do some extra steps. So I'm going to reorganize here. For that case, we need to draw a ice table. And I'll show you how to do it. So this is your ice table. Initially, you have 0.10 molar of soluble Pb2+ that comes from the soluble salt, and nothing of this. The change, therefore, is going to be whatever comes from the insoluble salt, which is X Pb2+, and 2X F-. At the equilibrium, we'll have whatever is initially that was soluble plus whatever comes from the solubility of the salt, which is 0.10 plus X, and 2X for the F-. We plug that into the expression, and we find the X. That's what we want to know. You reorganize everything. And we know the value of KSP that's given. Yeah, it doesn't show here, but definitely you will need to find it. We go to the tables somewhere because we need that number, and this is given on tables. So if somebody asks you to do this, you say, okay, can I have the KSP? Or sometimes you go a place to take the test, that they put at the end of the test a bunch of papers, data tables, and you are not allowed to ask questions. So you go and find your data on the papers that are attached to the exam. That shows that you know what to do. So this is the KSP for that insoluble salt. We got this front table of KSPs. So we plug everything, and we just need to solve for X. Here is the expression. Once you simplify, solve for X, and X equals 2.99 times 10 to the negative 4. And that's the solubility of PbF2 in that solution. So what was the difference between this problem and the previous problem? Look at the solubility of PbF at the same temperature. Is 2.03 times 10 to the negative 3 moles per liter. Very little, right? 2.03 times 10 to the negative 3 moles per liter soluble. That is in pure water. In pure water. Then we did the same salt, but not in pure water. We added to a solution containing a common ion. In this case, the common ion is Pb2+. Look, this soluble salt, once dissolved, produces an ion that is common to your insoluble salt. That's what I said at the beginning. In the container, you will have two different sources of Pb2+. One that comes from the soluble salt, and it's going to be complete because we have a very soluble salt. If you have a solution of 10 molar of that, that means you have 0.10 molars per liter of the ion. And the other source of Pb2 plus comes from the little solubility of the insoluble salt. And let's compare the two results. Let's remember the first one was 2.03 to the negative 3. 2.03 2.03 times 10 to the negative 3. Thus, dissolving PbF2, let's use a different color, this impure water. The solubility is that. Now we dissolve that in a solution, in this solution, that means that one contains a common ion. The solubility for the same substance at the same temperature is 2.99 times 10 to the negative 4. So what happened? That's called, that effect is called a common ion effect. How did it affect? The salt is less soluble if the solvent already contains an ion of the salt. It's called the common ion effect. And we see it here. You see, the solubility decrease. And that makes sense. How do you explain that? Le Chatelier's principle. So if we remember Le Chatelier's principle and we apply it to that, let's write it here again. PbF2 solid in equilibrium with Pb2 plus aqueous plus 2F minus aqueous, and produces X and 2X. But in the second case where we have the common ion, the solution already contained 0.10 molar of this. So basically you are adding a product, one of the products, the common ion, and what will happen with the equilibrium? The equilibrium shift to the left, pushing this, more of this to react with more of this to go to the left, because you are breaking the equilibrium by adding extra of one of the components, the common ion. So yes, it's proven. So don't forget that. And how do you recognize you need to do common ion? Well, because one problem just tells you find the solubility. That means you are solution pure water. And the other type of problem tells you you are adding the salt in a solution, and you look at the solution, that solution contains at least one common ion. It could be the cation, it could be the anion. That is common. So I give you this example so you can do it yourself, but don't cheat. Here's the answer, don't cheat. Do it yourself, use exactly the same thing procedure we did before, and then compare to my answer. Here is another one, it's common ion, because notice that you have the insoluble salt and adding to a solution containing a soluble. In this case, the common ion is F, the fluoride. This is the answer. Sometimes, if that process of adding a insoluble salt into a solution that contains common ion decreases the solubility of the insoluble salts, we have a situation where we can increase the solubility. If you can remember one of the experiments, one of the demonstrations I did on the first lab, for example, when we had the zinc nitrate and I added sodium hydroxide, that forms a precipitate. And then I kept adding hydroxide, and what happened was the precipitate disappeared. That means increase the solubility. Why? Because the zinc ion formed a complex. So that's one way to increase solubility. Metal ions are Lewis acid because they have positive charge, so they want pair of electrons. And that's why they form that covalent bond with the ions of neutral molecules to form the complex. And we'll use that to increase the solubility. I have one example here. The copper, I think I did it too. As a demonstration, copper 2 plus, we use copper sulfate with the blue solution. Then we added water, and that forms a complex. A complex contains a metal ion, which is called the ligand. Sorry, the ligand is the one that attaches to the metal ion. And the ligand is the one that is donating the pair of electrons to the Lewis acid, which is the metal ion. And that will form the coordination compounds. Because the bond, this type of bond is called covalent coordinate. So they are coordination compounds. Covalent coordinate means two species are sharing a pair of electrons, but the pair of electrons belongs to only one of them. This is one example of that. We can increase the solubility of copper 2 ions by adding a neutral molecule like ammonia, and it will create this nice, colorful copper complex. As you can remember, the color of this was a beautiful deep blue color. This is the formation of a complex. When we write the equilibrium expression, you will find a constant, and that constant is called constant of formation of complex. And that also is given on tables. So here we have another example where we have the copper complex with ammonia. In aqueous solutions, it breaks down into ions, and we can write the constant of formation expression for that, and this is a constant that is given, and we can find this on tables. The inverse of that is what we call the constant of instability. Sometimes it's useful. It's just the inverse of the first one. Let's check one application of this. It says calculate the solubility of silver chloride in 0.10 molar ammonia. So when you see this ammonia solution and it's not common ion, so you know this is a different problem. So you dissolve in silver chloride, in this solution, and notice that ammonia is not common ion. So it must be something different. And we remember this is a neutral molecule, it has a pair of electrons, so this makes a good ligand. That can attach to the metal ion. This will form Ag plus Cl minus. This is the solid, this is the aqueous, only one. This is the aqueous, Cl minus. So this makes a good Lewis acid ready to accept a pair of electrons from here. That will form a complex. So you realize we have a complex. For a complex situation, we just need to do one extra step, but it's not complicated. I'll show you on the here. We have to write two equations. First one for the solubility of Ag plus, and we write the expression. Ksp equals concentration of Ag plus times concentration of Cl minus from the first expression we know how to do. And this is the value. This is the value for the Ksp. But we need to write the second equation for the formation of complex. So once this is formed, and since we have ammonia in the solution, the Ag plus will react with the ammonia to form this complex. We write the equilibrium expression for that, which is the expression of formation of complex. And we know the K of formation, which is given also. Those values are given. So we have two equations and two constants. Then we add the two chemical equations. We add equation 1 and equation 2. Talking about chemical equation. So 1 plus 2 will give you this. Right, so because we have AgCl on this side of the equation, and then we have Ag, but Ag is on both sides, so we cancel those two. And then we have 2NH3, which is here. Now on the other side, we have Cl minus here, which is this. We have Ag and H3 two times, and that's it. And we write the expression of this, the new equilibrium constant for the new expression. And we know using operations of equilibrium constants that when we add two chemical equations, the only thing we need to do is to multiply the equilibrium constants for each one to find the new Kc. So you do that, and we get, that means this times this will give you the value of the new Kc, which is this one. Once we have the expression, we can find the solubility or any of these concentrations that are in the formula. Usually, we know this concentration because that was given. So we just need to find that one. And we do the ice table again. Use the previous equation, solve for x, and you find that x equals 4.5 times 10 to negative 3. And x represents the molar solubility of the complex. If we compare that to the solubility of silver chloride in just pure water, the first one we did at the beginning, let's compare this number, the solubility of silver plus forming the complex, with that of silver plus just in pure water. Look, we produce the ratio, and we find that the solubility of with the complex is 392 times bigger than the solubility in pure water. Also, if we know the values of KSP and the ion product, we can make predictions if precipitation will occur when we add two solutions. So this is the key. If the ion product Q is bigger than KSP, then the solution is supersaturated and precipitate will form. So remember, the ion product is similar to the reaction quotient. So you plug into the expression the initial concentrations. Doesn't need to be the equilibrium concentrations. With the ion product, I'll show you one example. Equals KSP, so the solution is saturated and no precipitate will form when you mix the two solutions. And when the ion product Q is less than KSP, no precipitate will form. So let's see this case. Let's solve this one. It says a solution is prepared by adding 700.0 mL of 4.00 times 10 to the negative 4 molar cerium nitrate, cerium-3 nitrate. So let's put that solution over here. How many mLs? We have 750.0 mLs. And the concentration is 4.00 times 10 to the negative 3 molar. And the compound is cerium-3 nitrate. That's beaker 1. In beaker 2, we have 300 mLs, 3.0 mLs of, the concentration is 2.00 times 10 to the negative 2 molar of potassium iodate. KiO3. So we're going to prepare a solution using these two solutions. The question is, will cerium iodate, cerium 3 iodate, that has KSP 1.9 times 10 to the negative 10 precipitate? When you put these two solutions together, that means we are going to pour that and that, everything together into another container. And the question is, will you see a precipitate? Do you have enough concentrations here to make a precipitate? Because definitely it's going to be a precipitate if we have the right concentrations, because this is insoluble. How do you know this is insoluble? Because it has a KSP. The problem is giving you a big hint. The problem is telling you this compound may precipitate because it's insoluble, because it has a KSP. Remember, only insoluble salts have KSP. So the reaction will be, let's do the reaction. Cerium 3 nitrate. Aqueous is soluble because it's nitrate. All nitrates are soluble, plus potassium iodate is soluble also because all potassium salts are soluble. Will form, this is a displacement reaction. So we have cerium iO3 3 times solid, because this is not soluble, plus potassium nitrate, KNO3, aqueous. Of course, it's potassium soluble, it's nitrate is soluble. Now, the stoichiometry. So we have 3 of those, that means we need 3. Nitrates there. And we need 3 iodates and 3 potassiums, and that's the 3 here. So it's balanced now. This is soluble, this one. This is soluble, this one. But when we put them together, there is a chance that we have the right concentrations to see this precipitate form. It will form only if they both together are able to make a saturated solution. If the solution is not saturated of this compound, the compound will not precipitate. Will still be soluble. We don't have to worry about this because this is a spectator ion. So let's see, let's do the calculation. So we need to find the concentrations. First, let's write the solubility equation for cerium for the insoluble salt. Solid in water will form an equilibrium with cerium 3 plus aqueous plus 3 iodate aqueous. And the equilibrium expression for this, KSP equals concentration of cerium 3 plus times concentration of IO3 minus cubed. And we know this number. The KSP is 1.9 times 10 to the negative 10. In order to make the prediction, we'll also need to write Q. And what is Q? It's similar to reaction quotient, but here we are going to express it. Has exactly the same shape as KSP. Exactly the same. CE cubed. We don't know yet because we need to find these values. Exactly the same shape as the KSP, but now receives a name of Q. Remember reaction quotient? So what is the difference? Why this is called different? Yes, because here we are going to write initial concentration, whatever is here, and whatever of this is here, the initial concentration, before the reaction. So we're going to plug those numbers here. We're going to find the numbers from here, plug it here, compare these two numbers, and if this number is bigger than this, then precipitate will form. If this number equals to this, no precipitate will form. If this number is less than this number, no precipitate will form. Sorry. So let's find these initial concentrations. We don't have to find the equilibrium concentration because we already know the KSP. So remember, that's the only thing we want to know. We want to know the KSP to compare with Q, the ion product. So let's find the initial concentrations when it's soluble. We need to find how many moles of this is here before you combine. So how do you find that? This is the formula of molarity, right? So moles of cerium 3 plus equals molarity times value. The molarity happens to be 4.00 times 10 to the negative 3 times the volume, which is 750 ml. We need to convert that into liters. That means 0.75. We do this multiplication. I think I have the results on the next page. Right? Let me check. No. Okay, so let's do it here. So we have number of moles. I hope you are doing the same calculation at the same time with me on your calculator. So we have 4 times 10 to the negative 3 times 0.75. And I got 3.0. 3.0 times 10 to the negative 3. That's the number of moles. And the final concentration, molar concentration of C3 plus will be moles over volume. And what is the final volume once you put everything together? That will be the final concentration. Because remember here you have some in 750 ml solution, but when you put it here, then you have more volume, so the concentration will change. It's not the same initial concentration. That's why we are doing this. So the total volume here is 750 mLs plus 300.0 mLs. So that gives a total volume as 1050 mLs, 0.0. So that's the total value. And we do that 3.0 times 10 to the negative 3 divided by, in liters, that will be 1.05 liters. So that concentration is 3.0 times 10 to the negative 3 divided by 1.05. And that is 2.86 times 10 to the negative 3. Okay, we find the concentration of cerium here, the initial concentration, using the final volume. So that's the new concentration. Let's do the same thing. Let's find the concentration of iodate here, using the total volume. I'll do that calculation here on top. Similar. So we find the moles of iodate equals molarity times volume. The molarity is 2.00 times 10 to the negative 2 times the volume, which is the volume we have initially here, 0.3 liters, 0.300 liters. And that gives you 2.0 times 10 to the negative 2 times 0.3. That is 6 times 6.0 times 10 to the negative 3. That's the number of moles. Now let's find the new concentration of cerium of the iodate once we combine everything together, because the volume will change. So the concentration of iodate final will be these moles over total volume. So that will be 6.0 times 10 to the negative 3 over 1.05 liters. So we have divided by 1.05. That is 5.71. 5.71 times 10 to the negative 3. So we had the two concentration. Now we can plug that over here to find the ion product, to find Q. Let's do that. So the concentration of cerium is 2.86 times 10 to the negative 3 times concentration of iodate 5.71 times 10 to the negative 3 cubed. Let's not forget that. And that is, let me see, and I have the cube function there. I'm trying to find my Q function in my calculator. So that will be 1.86 times 10 to the negative 7 times 2.86 to the negative 3. So the final number is 5.3 times 10 to the negative 10. Same order the magnitude as the KSP, right? And let's compare the two numbers. Which one is bigger, KSP or Q? Here we have 1.9 times 10 to the negative 10, and here we have 5.10 times 10 to the negative 10. So we said that Q is bigger than KSP, therefore precipitate will form. All right, so that's how we solve this type of problems. The rest is just similar situations. And I want to leave it here. This is what we did in your experiments 2 and 3. You were using qualitative analysis using selective precipitation to figure out the composition of a mixture to find your known group 1 metals and unknown group 1 metals, and then you did it with the group 2 metal ions. All right, so I'll leave it here. This is the end of this chapter 17. The next chapter I'm going to discuss is going to be thermodynamics. And then we'll do electrochemistry, and that will be the end of the course. All right, so see you next time.